In this video, I'll show you how to use the Ordinal Regression program. I'm going to come down to the button where it's located, which is here, and I click on it. When I do, a set of directions appears in the description box. I won't go over those with you here. And when we input information, we'll be inputting information into the input values box for the Ordinal Regression. Because the program uses raw data, I have to go get the data file. So to do that, I'll click on Choose File. I have to scan to the directory where the file is located. It's in RET. In this case, the file is going to be chap13r.txt. This lists the variables that are in the data file and that I'll be using. And then up here, I have to give the full folder path in order to find the file. Now, having access to this information is important because R is case sensitive and we need to enter in the variable names using the exact capitalization as well as the exact spelling of each variable. The data I'll analyze is from the numerical example in Chapter 13. I'm going to use a simplified version of it, as my primary goal is to show you the different features of the program rather than to conduct a comprehensive analysis. The intervention is a program designed to teach clinicians how to be better clinicians. And as part of the interventions, clinicians are taught how to better set common goals with the client about treatment. This is known as goal alignment. Clinicians also are taught how to better negotiate and reach agreement with clients about what needs to be done to accomplish those goals. This is called task alignment. Finally, clinicians were taught how to develop a positive bond with the client to promote client motivation and adherence to protocols. This is known as bonding. Clinicians in both the treatment and control groups were independently rated after the program on how well they did these tasks, with the hypothesis that clinicians in the intervention condition would be higher on each construct than those in the control condition. The ratings by the observers were made on multi-item 7-point agree-disagree scales that were averaged across items. Each item was scored -3 equals strongly disagree, -2 equals moderately disagree, -1 equals slightly disagree, 0 equals neither agree nor disagree, 1 equals slightly agree, 2 equals moderately agree, and 3 equals strongly agree. Item scores were averaged. The higher the score, the higher the goal alignment, task alignment, and bonding. I treat each of these multi-item total scores as continuous, interval-scaled mediators. Client symptom improvement after being treated by the clinician was the primary outcome. It was measured on a crude 4-point ordinal metric. The scale was completed by an independent clinician who rated the improvement of the client as 1 equals no change or got worse since treatment initiation, 2 equals minimally improved since treatment initiation, 3 equals much improved since treatment initiation, and 4 equals very much improved. I will focus on an analysis that relates the 3 mediators to the outcome to gain perspectives on the relevance of the mediators to the outcome. The 3 mediators are GA2 for goal alignment, TA2 for task alignment, and BD2 for bonding. And IMP3 is the variable for improvement. I will regress symptom improvement onto these 3 mediators. Normally I would include covariates, and I do so in the book chapter, but I exclude them here to keep things simple. Now, M+ offers a proportional odds ordinal regression model, but there are other types of ordinal regression you can do. I discuss these other types in my book. One of them is called adjacent category regression, and I'm going to illustrate it here. It uses logistic regression, but as you'll see, I focus on probabilities in addition to the more typical odds ratios that people use with logit models. The adjacent category model uses the following 3 binary equations. First, I predict the log odds of being in category 2 versus being in category 1 of the symptom improvement scale. This is the equation I would use as I predict that from goal alignment, task alignment, and bonding. Second, I predict the log odds of being in category 3 versus being in category 2. And finally, I predict the log odds of being in category 4 versus category 3. Each one of these is an adjacent category, and I'm predicting that people are in a category higher than the target category as a function of the predictor variables. The equations as a whole predict the log odds of moving up one category on the improvement scale as a function of increases in goal alignment, task alignment, and bonding. As I discuss in my book, in ordinal regression, we make the assumption that the coefficient for moving from category 1 to category 2 as a function of goal alignment, that is B1, is equal to the coefficient for moving from category 2 to category 3 for goal alignment, i.e. B4, which also is equal to the coefficient for moving from category 3 to category 4, or B7. This is known as the parallel coefficient assumption. It underlies all forms of ordinal regression. Given this assumption, I only need to report one coefficient for each predictor, because once I know the value of one of them, I know the value for all of them. For example, once I know the value for B1, I also know the value for B4 and B7, given the parallel coefficient assumption holds. This assumption is also made for task alignment and for bonding. I'll show you in a bit how to test the assumption using the current program, but let's first conduct the analysis with the assumption invoked. Okay, the first thing I need to do is to specify the type of model that I want to estimate. The numerical options are given in the description box. If I want to see a reminder of what's in the description box, I can click on the toggle button down here and it'll show me. And the option 1 is the adjacent category model, so that's the one we're going to use. And that's the default model here, so I'm just going to go with that. Next, I have to specify if I want a forward or reverse solution. The forward versus reverse option allows you to specify the direction you want the analysis conducted. For a forward solution, your focus is on IMP3 categories ascending upward, i.e. higher scores are better. So the analysis is 2 versus 1, 3 versus 2, and 4 versus 3. For a reverse option, your focus would be on IMP3 categories descending, i.e. lower scores on the outcome are assumed to be better. So the analysis is on comparing 1 versus 2, 2 versus 3, and 3 versus 4. We're going to use the forward solution here. See my book for details. Again, if I look down here, I can see 1 is forward, 2 is reverse. And then finally, I can use either a logit or a probit model. And in this case, I'm going to go ahead and use a logistic model. Here, I specify the % confidence interval I want, and the default is 95. I'll explain these other boxes to you later, but the main thing is I have to enter in the equation that I want to focus on here. So I'm going to unerase that, and following what's in the direction box, I'm going to specify the regression equation using R format. In R formatting, the outcome variable is listed on the left, and instead of an equal sign, we have a little tilde sign, a little wiggly line here, and then we list the predictors without listing the coefficients and using a plus sign between the predictors. Okay, I click on register input to generate the R syntax. The R syntax is generated here. I copy that to the clipboard. I start R, and I hit Control V up here in order to paste the syntax, and as I paste it, it'll execute. Now the input is in red and the output is in blue, so we want to focus on the blue. And I'm going to come up to where the output starts, up here. The total sample size is 600. This information here gives you the frequency distribution for the outcome variable, so there are 102 people in category 1, 187 in category 2, and so on. And this translates those frequencies into percents. Here are the traditional fit indices for the model. I do not discuss those here. You can see my book for details. I will, however, make use of them in a little bit. If you're a fan of pseudo R-squares, you can use this information to calculate them. Here are the logic coefficients for the model. And down here I present the coefficients again with the confidence intervals around them. And then I express the coefficients as odds ratios also, which is what most people interpret. For example, I can see for goal alignment that it was statistically significant. I come back up here and I see GA2. There's the statistical significance and the critical value for it, the z-test. And the coefficient translated into an odds ratio was 3.367. That means that for GA2, for every 1 unit that GA2 increases on its -3 to +3 metric, the odds of being in the next highest category increase by a multiplicative factor of 3.37. That is, it's over 3 times more likely you will be in the higher adjacent category with a 1 unit increase in GA2. As I said, the result is statistically significant, and you can use the confidence intervals to form a margin of error around that. You can see my book for details. Now recall that I made an assumption of equal coefficients for a given predictor across the binary equations. Turns out I can relax that assumption for one or more of the predictors. So let me close R and go back and show you how to do that. I have a box here called unconstrained, and that will allow me to specify variables that I want to relax the constraint for. For example, if I want to relax the constraint for TA2, I enter it here, and the model will then estimate separate coefficients for the 3 different logistic equations for it. If I want to unconstrain 2 variables, I can do that. I would just put GA2 and TA2 as the 2 variables I want to unconstrain, and I can unconstrain all of them if I want to. Let me show you what happens if I just unconstrain TA2. So I'll hit register input. I'll copy the syntax of the clipboard. I'll start up R. I'll hit Control V. And now it does the analysis with TA2 coefficients unconstrained. Gives you the sample size again and the frequency distribution for the outcome variable. Here's the model fit for the unconstrained model. I'll come back to that in just a minute. Here are the coefficients, and notice now I get 3 coefficients for TA2 instead of just 1, because I've relaxed that assumption. So these are the logistic coefficients here, and all 3 of them are statistically significant. And then I get the coefficients and their confidence intervals, as well as the exponents of the coefficients, or the coefficients expressed as odds ratios here. And you can see the 3 different odds ratios. They're not that discrepant when I look at the 3 of these. So the assumption of equal coefficients might be viable in this case. Now let's go back and look at the model fit statistics for both the fully constrained model that I initially ran as well as this model here. And the question is whether or not the fit of the unconstrained model is significantly better than the fit for the fully constrained model. If the fit is not much better, then I don't need to relax the assumption. But if when I relax the constraint I get a much better fitting model, then that suggests that I do need to relax it. Now we'll look at this from different vantage points, but one of the things I can do is a significance test of the difference in model fit using the log likelihoods. So making use of these 2 statistics here, I can do a significance test of the difference in model fit. And I would do that using the log likelihood difference program on my web page. Let me show you. I come back to the programs. I'll go up to the index of programs, and here's a program called the log likelihood difference test. So I'm going to click on that. Again, there's a set of instructions in the description box on how to do that. And what I do is I put in the log likelihood for the constrained model here and the number of parameters in it. And then I put in the log likelihood for the unconstrained model and the number of parameters in it here, and then it'll do the difference test. So the log likelihood for the constrained model was minus 554.5541. So here I need to specify the number of identifiable parameters in each model, and this will just equal the number of terms on the right hand side of the equation. Practices vary somewhat for identifying the number of identifiable parameters, but for our purposes that heuristic will work just fine. So in the fully constrained model I had a total of 6, so I put in 6 here. And in the unconstrained model, again, if you just go back and count up the number of predictors plus the intercept terms, that's what goes in there. The log likelihood for the unconstrained model was minus 553.4491. I click on register input to generate the syntax. I copy that to the clipboard. I'm going to come back here and close R and then reopen it. I like to do that to always start fresh. I'll paste it with Control V, and the chi-square difference in fit between the two models was 2.21, had 2 degrees of freedom, and the p-value was 0.33. So there was a non-significant difference in the fit of the two models, which is consistent with then the parallel coefficient assumption. Let me close this and go back to the statistics. Okay, another perspective on this is to look at the Akaike information criteria, the AIC or the BIC. And in general, the lower the value of the AIC or BIC, the better the fit of the model. And we use these information fit indices to compare the relative fits of two models. And we prefer the model that has the lower AIC or BIC. And both the AIC and the BIC have penalty functions built into them that penalize a model for having more parameters. And the unconstrained model has more parameters in it than the fully constrained model, so there's a little penalty function for it. And you can see that the AIC for the fully constrained model is lower than that for the unconstrained model, and that's also true of the Bayesian index. The penalty function is a little harsher in the Bayesian information criterion than in the AIC. So this also is consistent with using a fully constrained model for the TA2 predictor. In general, two models are said to fit about the same if they are within 2 units of the AIC of each other, which is the case here. And that's also roughly true of the BIC. It's a little harsher. 2.2 is the guideline that's there. But the fact that the models are within 2 units of each other suggests that they predict about equally well. Here are the results when I did the same test for the GA2. That is, instead of focusing in on TA2, I focused in on goal alignment, GA2. It turns out in this case it's a little more complicated because when I did the log likelihood test, the difference in model fits was statistically significant at p less than 0.04, which suggests that there is a difference between the models. If I added some covariates to the model, the statistical significance moved to 0.07. So interestingly, if you include covariance in the models, that can change the result. But the two p-values are kind of close to one another. One is just a little bit less than the 0.05, and the other is just a little bit higher than the 0.05. If I look at the AICs, I now see that the AIC for the unconstrained model is lower than that for the fully constrained model. But for the Bayesian index, it's just the opposite, because Bayes is giving a harsher penalty function for those extra two parameters here. So I have kind of conflicting evidence here. Let me show you the output on the run, because that will also give us some perspective on things. I'll go back up to the index. I'll click on the Ordinal Regression program. I'll come down here. I'll re-specify the equation. I'll unconstrain GA2. I'll register the input. Copy that to the clipboard. I'll start R. Hit Control V. Again, I can work my way down from the top, but what I want to highlight here are the odds ratios for the three coefficients for goal alliance. And here it's 6 times more likely with a 1 unit increase in GA2 that you'll be in category 2 versus category 1. Here it's only 2.5 times more likely, roughly, that you'll be in category 3 versus category 2. And here it's about 3 times more likely that you'll be in category 4 versus category 3 with a 1 unit increase in GA2. So there are some disparities here, and the question is, are they theoretically coherent, and should we go ahead and relax that assumption, or should we go ahead and keep the coefficients the same? So to show you the rest of the program, I'm going to work with the fully constrained model, but you can see that it's a little bit tentative here with goal alignment. Okay, I'm going to close R. I'm going to come back up here. Now suppose I want to evaluate the impact of GA2 on the outcome using probabilities rather than odds ratios or multiplicative factors. I can do this using the profile analysis, which are these two boxes, which I'm going to show you now. What I can do in the profile box is I can specify and compare different predictor profiles. So for example, one profile I might have, which I'll put in the profile 2 box, is where a GA2 has a score of 0, where TA2 has a score of 0, and where BD2 has a score of 0. And I can then see what's the probability of being in each of the 4 categories for individuals that have this particular profile of predictor scores. And it turns out in this case the mean value of GA2, TA2, and BD2 is right around 0. And so I'm actually putting in kind of typical scores on GA2, TA2, and BD2. And scores of 0 also map onto the neither agree nor disagree part of the metric of each of these scales. Now I'm going to contrast that with a profile where I increase GA2 by 1 and hold TA2 and BD2 constant at their value of 0. So in ways what I'm doing is I'm comparing the effect of increasing GA2 by 1 unit, holding constant the other predictors at scores of 0, and then I'm going to be, as you will see in a minute, looking at the probabilities. Now when I compare the two profiles, I have to bootstrap the standard errors for each profile and to do the comparisons. So I have to specify the number of bootstraps that I want. You can see my book for a description of bootstrapping. The default is 300 bootstraps. You can increase that up if you want more accuracy. But this is pretty program intensive and it takes a long time to run, so you have to be very patient if you increase the number of bootstraps. I click register input. I come down and I copy the syntax. I'll I'll start R, and I hit Control V to paste it. Now what happens in the middle of as it's executing, this is where it's doing the bootstrapping. And this is going to take a while. It's going through a loop and repeating the program 300 times. So you have to be patient, and this will eventually work its way through, and the results will come up. And here they are. So you get the standard output that you would normally get from the traditional runs without the profiles. But now we get at the very bottom the profile analyses, and those are here. So this is the first profile where GA2 was equal to 1 and the other two predictors were equal to 0. And this is the second profile where they were all equal to 0. And then this is the difference between the two profiles. And this is the probability that individuals with this profile are in category 1 of the outcome variable, or the proportion of people that are in category 1 of the outcome variable who have this profile. This is the proportion of people that are in category 2, in category 3, and in category 4 for this particular profile. And the same is true here for the second profile. These are the standard errors and the confidence intervals around these probabilities for each one of these. And then this is the difference between them. So I can see that when GA2 is equal to 0, TA2 is equal to 0, and bonding is equal to 0, about 25% of the cases are in the lowest category, which is no change or got worse since treatment initiation. But when I increase GA2 by 1 unit, that goes down to 0.05, which is a good thing because now more people are responding to the treatment. And here's the difference between 0.25 and this 0.05 figure here, the standard error and the confidence interval. And it's statistically significant because the confidence interval doesn't contain the value of 0. So we can see by looking at these differences that if I raise GA2 by 1 unit, the proportion of people in category 1, which is no change or got worse, is going to go down by about 0.20. The proportion of people who are in category 2 is going to go down by about 0.14, and category 2 is only minimally improved since the treatment condition, and the proportion is going to go up by close to 0.29, which is the category much improved since treatment initiation, and category 4 is very much improved from treatment initiation. And we're going to see a statistically significant increase in these two categories and a statistically significant decrease in the proportion of people in these two categories. So this is coming at things from the level of probabilities and probability differences rather than odds ratios. And I discuss in my book why I'm a little bit uncomfortable with focusing just on odds ratios. And I think it's better or helpful to also take a look and see what's happening at the level of the individual categories and the probabilities or proportions. And this allows you to do that. Since I first made this video, I've expanded the program to allow you to explore 4 profiles rather than just 2 in the profile analysis. This allows you to do a more comprehensive analysis and also to apply the framework for discrete change as described in the video for the program called Compare Discrete Change. Watch the video for that program and read the corresponding chapter in my book on ordinal outcomes for ways you can strategically select your profiles to analyze moderation. Okay, that's it. Thanks a lot.